Our next discussion is about deploying SparseLand to signal and image processing needs. We have just defined the SparseLand prior and seen how it is related to known alternatives. This model poses a strong and flexible union of subspaces structure that has some interesting ties with GMM. It is time to revisit many of the tasks that signal and image processing might lead us to and see how SparseLand should be deployed in each in order to provide you with the full picture. We start with the concept of transform. Suppose that X is a SparseLand signal being built as D times alpha, where alpha is sparse. Our goal is to apply an effective transform on X. Why are we doing this? Why are we applying a transform? Because we want to explore this signal in order to better understand it. An ideal transform would lead to a set of independent coefficients while concentrating most of the energy in as few of them as possible. Well, think about it. What could be better than the vector alpha itself, which generated X as the transform coefficients? It is the sparsest possible explanation of X. Its elements are independent, and beyond these, it will be found by solving this problem for which we have algorithms and some theoretical guarantees for their success. So we have the perfect answer to the quest for transforms for SparseLand signals. Moving on, we now aim to denoise a SparseLand signal. We get Z, an epsilon noisy version of X0. Our goal is to remove the noise from Z and get as close as possible to X0. Our task translates into a projection onto the model. Exploiting the specific structure of SparseLand signals, this is done by solving this problem that we have referred to as P0 epsilon. It searches the sparsest alpha to explain Z to within an epsilon error. Once this alpha hat is found, we multiply by D and get the denoise signal. If alpha hat is close to alpha 0, we will get very strong noise attenuation, just as hoped for. Well, wait a minute. We have theoretical guarantees that promise exactly this behavior for a variety of pursuit algorithms, so denoising of SparseLand signals is definitely within reach. What about more general inverse problems solved for SparseLand signals? In this case, there is a degradation operator, age, that needs to be taken into account. Our strategy will be to identify the alpha that generated the signal and use it to create the restored result. This will be done, just as before, by solving an instance of P0 epsilon. The only difference is that the effective dictionary now is age times D. And again, we can rely on the availability of pursuit algorithms and the theory that guarantees their good performance. Once alpha hat is found, its multiplication by D leads to the restored signal. What about compression? We are given X0, a SparseLand signal, and we aim to compress it. Solving P0 epsilon while varying the value of epsilon gives us the best rate distortion curve for this signal. Why? Because it seeks the simplest explanation of the signal while allowing a fixed distortion epsilon. The resulting curve looks like this, giving a signal energy for a 0 rate and the cardinality of alpha 0 for a 0 distortion. Here again, we find ourselves in a need to solve P0 epsilon, and here again we can rely on the pursuit methods and the theory that accompanies them. Let's talk about signal separation, shall we? X1 and X2 are two SparseLand signals emerging from two different models, the first using D1 and the second using D2 as their corresponding dictionaries. We get a noisy sum of them, Z, and our goal is to decompose this signal into its three parts. Our strategy, as before, is to identify the representations that generated the two original signals. This is done by solving this problem. We search for the sparsest alpha 1 and alpha 2 such that D1 times alpha 1 plus D2 times alpha 2 is up to epsilon away from Z. Once these alphas are found, their multiplication by the corresponding dictionaries lead to the desired separation. This whole task can be rephrased to look like a classic P0 epsilon problem in which dt is a horizontal concatenation of the two dictionaries and alpha t combines the two alphas vertically. So again, we find ourselves in a need to approximate the solution of P0 epsilon. Let's present the concept of compressed sensing. Suppose that x0 is a SparseLand signal that we aim to work with. However, we do not want to measure it in full, and therefore we create a projected version of it of low dimensions. Capital P is a projection operator, in which the number of its rows, lowercase p, is much smaller than the signal dimension n. In order to be practical, let's assume that the projection is accompanied by an additive noise. Compressed sensing asks whether we could effectively recover x0 from the projected noisy measurements z. The answer is positive, relying on the solution of the p0 epsilon all over again. Observe how close this application is to the inverse problem setting. The only difference is in the fact that here we have control over the projection operator p, something that could help increasing our chances of a good recovery. In all the tasks that we described, and in many others, it is p0 epsilon that stands at the center. For this optimization problem, we know two key things. First, it is theoretically well-founded and well-behaved. And secondly, practical and effective numerical methods for solving it are available. Thus, the bottom line is that the SparseLand model and Prio are well-founded and well-equipped, paving our way to real-life applications. Just before we conclude this story and start talking about actual applications, a word of caution. From the description given above, you might get the impression that from here on, everything will be simple and near trivial. All that needs to be done is to solve p0 epsilon and everything will fall nicely into place, right? Well, you couldn't be more wrong. As we move to true applications, we will discover that there are various ways and a lot of flexibility in practicing SparseLand. These are not necessarily bad news. This implies that there is a lot of room for ingenuity and originality also in the applicative part of the work in our field. We will meet this wealth of options as we sweep through a series of image processing tasks.